When artificial intelligence meets global navigation satellite systems, or GNSS, an entire new landscape of intelligent positioning and perception begins to emerge. For decades, GNSS has provided the backbone of global positioning, timing, and navigation. It has been extraordinarily successful in open sky conditions where signals from satellites are strong, multipath is minimal, and models of atmospheric delay behave predictably. Yet every researcher and engineer knows the limits. In urban canyons, inside vehicles, under dense foliage, or in complex indoor-outdoor transitions, the classical GNSS receiver starts to fail. Position solutions become noisy, biases appear, and the system becomes unreliable for the centimeter-level accuracy that modern applications, such as autonomous vehicles, precision agriculture, and pedestrian navigation demand. This is precisely where the modern wave of machine learning and artificial intelligence begins to play a transformative role. At the heart of the problem lies uncertainty. GNSS measurements pseudorange, carrier phase, Doppler are corrupted by a mixture of stochastic and deterministic errors. The traditional toolset for dealing with them has been probabilistic estimation, Kalman filters, particle filters, and Bayesian smoothing methods. These rely on explicit models of motion dynamics and sensor noise, but the world as we observe it often violates these models. Human walking patterns are nonlinear and context-dependent. Multipath errors are not Gaussian. They depend on building geometry, antenna pattern, and environment dynamics. The promise of AI is that we can learn these models directly from data rather than predefining them. In the last decade, researchers have begun to fuse GNSS with inertial sensors, cameras, barometers, and even Wi-Fi using deep learning architectures. For example, recurrent neural networks can learn temporal dependencies between inertial measurements and satellite signal quality indicators to predict position updates even when satellites are blocked. A convolutional neural network can analyze the sky view image or power spectrum of GNSS signals and classify whether the current environment is likely to produce multipath transformers. Those architectures born in natural language processing are now being used to attend to sequences of satellite observations, learning which signals are trustworthy at each epoch. The evolution is moving from explicit modeling to learned modeling. To understand the fusion process, consider the typical GNSS measurement model. The pseudorange to satellite eye is equal to the geometric range between the receiver and the satellite plus clock bias, atmospheric delays, and noise. In a classical estimator, we linearize this relationship and solve for position iteratively. In a deep learning assisted framework, we can treat the residuals between measured and predicted pseudoranges as a training target. A neural network ingests contextual features, carrier to noise ratio, satellite elevation, Doppler spread, and inertial acceleration, and learns to predict correction terms. These corrections are then fed back into the positioning algorithm, reducing the residuals systematically. The approach does not replace GNSS physics. It augments it with learned context awareness. Another frontier is factor graph optimization, or FGO, a smoothing approach that models the entire trajectory as a graph of states connected by measurement factors. This framework already unifies GNSS, inertial, and vision data elegantly. When AI enters this domain, it acts on two levels. First, neural networks can learn the factor weights or noise covariances adaptively. Instead of assuming fixed variances for GNSS or IMU factors, the system can infer from data which sensors are reliable at a given time. Second, AI can learn to parameterize complex residuals themselves. Graph neural networks propagate information along the factor graph, learning representations of connectivity that traditional solvers treat purely algebraically. Experiments show that hybrid systems combining differentiable optimization layers with neural networks can achieve both interpretability and adaptability. Let us step into a practical example that many smartphone researchers encounter: pedestrian dead reckoning fused with GNSS. The phone's accelerometer and gyroscope provide relative motion, but their integration drifts rapidly. GNSS provides global updates but suffers from multipath and dropouts. A factor graph can link successive positions with PDR factors derived from detected steps and headings, and GNSS factors derived from pseudoranges. When AI joins, it can predict step length as a function of gait, phone orientation, and user context using a neural model trained on large datasets. It can also estimate when GNSS signals are degraded and adjust their weight dynamically. The result is a smoother, more reliable trajectory that remains accurate even in challenging environments, such as dense cities or shopping malls. Training such models requires data, and this is one of the largest challenges in AI GNSS research. Public datasets like the Google Smartphone Decimeter Challenge, Kitty, or Oxford Robot Car provide raw GNSS, inertial, and ground truth trajectories. Researchers build supervised networks that map raw features to positioning corrections. However, truly robust models need diversity, various cities, devices, antennas, and motion profiles. Self-supervised learning is therefore gaining traction. Instead of relying on labeled ground truth, a network can learn consistency constraints between sensors, minimizing differences between forward and backward predictions, or between GNSS only and fused estimates. Such self-supervised objectives enable learning from vast unlabeled datasets collected by fleets of vehicles or smartphones. Beyond localization accuracy, AI contributes to integrity and reliability assessment in safety-critical systems, such as autonomous aircraft. Or rail applications, it is not enough to estimate position. We must estimate confidence. Neural networks can output not only mean position but also uncertainty distributions, often modeled through probabilistic layers or Bayesian networks. These learned uncertainties feed into protection level calculations, allowing the navigation system to decide when to trust or reject a solution. Some frameworks even combine classical RAM receiver autonomous integrity monitoring with deep classifiers that detect anomaly patterns in satellite constellations. A related research direction explores signal domain AI. Instead of working on observables like pseudorange, AI models process raw intermediate frequency samples of GNSS signals. Convolutional networks can detect line of sight versus reflected components directly in the correlation function. Reinforcement learning agents can adapt receiver tracking loop parameters like bandwidth or integration time dynamically based on signal quality. These ideas bring the intelligence closer to the physical layer, potentially revolutionizing how receivers operate. Despite these exciting advances, there are major challenges that researchers must articulate clearly. First is generalization. A network trained in one city or with one receiver may not perform well elsewhere. Data normalization, domain adaptation, and transfer learning are critical research areas. Second is explainability. Classical GNSS algorithms are transparent. We can trace each error source. Neural networks, by contrast, are often black boxes. Hybrid models that embed physical constraints within the network, sometimes called physics-informed neural networks, aim to bridge this gap. Third is real-time performance. Factor graph optimization and neural inference are computationally heavy. Edge deployment on embedded platforms requires pruning, quantization, or lightweight architectures such as spiking neural networks or gated RENs. The interplay between AI and GNSS also raises exciting theoretical questions. For instance, can we view traditional estimation as a form of differentiable computation? If so, can we backpropagate through the Kalman filter itself and train parameters end-to-end? Researchers have shown that differentiable filters, where the process and measurement models are parameterized by neural networks, can outperform hand-tuned models in dynamic environments. This merges deep learning with classical estimation theory into a unified pipeline, sometimes called deep sensor fusion. Consider the implications for autonomous vehicles. A self-driving car must localize precisely even when GNSS is partially denied. AI-enhanced multi-sensor fusion provides the redundancy required for centimeter-level accuracy. Visual odometry, LiDAR maps, and GNSS corrections feed into an optimization backbone. Neural networks within that backbone learn to assess sensor trustworthiness in real time. When GNSS signals are weak, the network shifts weight to visual inertial constraints. When visibility improves, it leans back towards satellite updates. The resulting system is adaptive, resilient, and self-tuning properties that classical fixed-parameter filters struggle to achieve. Another dimension is collaborative or networked AI GNSS. Instead of each receiver operating independently, multiple agents share information. Machine learning models can infer local corrections based on spatio-temporal patterns of errors across a network. For instance, if several nearby receivers observe similar biases, the system can learn a regional ionospheric or multipath correction surface, with the expansion of low Earth orbit satellite constellations providing massive data bandwidth. Such cooperative AI GNSS networks become feasible, enabling cloud-based learning and edge-level inference. At the hardware frontier, specialized AI accelerators are being integrated into modern GNSS chipsets. These allow real-time inference for tasks such as interference detection, spoofing classification, or adaptive tracking. The combination of low-power neural processors and efficient algorithms opens the door to intelligent receivers that continuously learn from their environment. Imagine a smartphone that, after walking through a city for a week, automatically learns which streets produce multipath and preemptively adjusts its tracking parameters. Research is also exploring quantum and AI synergies within GNSS frameworks. Arquimia and similar companies are investigating how quantum sensing, extremely precise timing, and inertial measurement can be fused with AI algorithms for navigation without external signals. In such systems, machine learning models manage bias estimation and drift correction, effectively providing GNSS-like accuracy even underground or underwater. These developments suggest a future where the boundary between satellite navigation, inertial sensing, and AI perception becomes increasingly blurred from a methodological perspective. Evaluation and benchmarking remain essential. When presenting AI GNSS results, one must report metrics such as horizontal and vertical RMS error, 95% circular error probability, drift per distance traveled, and integrity risk. Cross-validation across datasets, devices, and environments is necessary to claim robustness. Furthermore, reproducibility, sharing code and data is key to advancing the field. Open initiatives like the Smartphone Decimeter Challenge have already catalyzed progress by providing standardized evaluation frameworks as this seminar approaches its conclusion. It's worth reflecting on the philosophical shift AI brings to navigation science. For decades, navigation was dominated by analytic modeling, derive equations, linearize, estimate. Now we are complementing that paradigm with empirical modeling, learn patterns directly from data, neither replaces the other. The future lies in their fusion. Physics ensures interpretability and safety, while learning provides flexibility and adaptation. When these two pillars cooperate, we obtain navigation systems that are both trustworthy and intelligent. By integrating learned models into physical estimation frameworks, we achieve unprecedented accuracy, resilience, and autonomy. The next decade will likely see AI-enhanced receivers, cloud-assisted cooperative positioning, and self-optimizing sensor networks that continuously learn from their experience,